And here's the solution to problem number 1 from exam 2. All right. So in this problem, we have a message signal M of t. It's got a baseband bandwidth of 60 kilohertz, and it's modulated up using amplitude modulation to 60.8 megahertz. All right. Then we're going to sample this, intentionally alias it effectively by downsampling at 600 kilosamples per second to form the received signal R of k. Okay, so the first part of the problem is to simply draw the spectrum of R, right? And so what we know is that we have R of t, and if we look at the Fourier transform of R, it's given by this diagram. And so if we wanted to modulate that signal, we take that shape, all right, and move it up to 60.8 megahertz. So this is frequency in hertz. Okay, and we can color that in with the same color. And if the original signal height was, if this value was m naught, okay, this would be m naught over 2. All right. So from there, we can take this shape and copy it and move it back to minus 60.8 megahertz. All right, so here is the Fourier transform of the signal, the received signal. Okay, next, you're asked to calculate the center frequency in hertz of R of k. And remember, R of k is intentionally downsampled at not high enough rate so that we get something that's a little more practical for digital signal processing. Okay, so what happens here is that you can come up with essentially the aliased carrier frequency. I'm going to call that Fc prime. And Fc prime is the original 60.8 times 10 to the 6th minus the original carrier frequency minus some integer multiple of 600 times 10 to the 3rd. Okay, 600 times 10 to the 3rd is the sampling rate. Okay, so what we know from the sampling theorem is that when we sample a signal, it replicates the spectrum every Fs. Okay, so Fs is 600 times 10 to the 3rd. All right, and so n is an integer value, and n is chosen so that Fc prime is in the Nyquist interval. So the Nyquist interval is Fs minus Fs over 2 to Fs over 2. So minus 300k to 300k. Okay, and so what we've done is we found, our examples in class is we found the exact value of n, not taken into account that n has to be an integer. So we're going to solve for ne, the exact value, so that we hit the upper edge of the Nyquist interval. And from there, we can round up to make sure that we come up with the value of n that actually works for aliasing this signal back into the Nyquist interval. Okay, so solving this equation for n and using the subscript e, we get 60.8 times 10 to the 6th minus the upper edge. We're setting this equal to 300 times 10 to the 3rd. So solving for n, we would get this expression. And when you solve for ne, you get 100.83. Okay, so the value of n that we use is the CEAL function. You round it up and you get 101. All right, so that lets us calculate FC prime. That'd be 60.8 times 10 to the 6th minus 101 times 600 times 10 to the 3rd. Okay, and so what we get for FC prime is 200 kilosample or kilohertz. Okay, so once you know that, we can then draw this picture, and we know the Nyquist interval is 300K. This is frequency in hertz, and minus 300K. The shape of the spectrum is the same as we had before, so it's actually scaled by the sampling period. But let's ignore that for now and just grab this shape and paste it. Okay, here we go here and here, where this is 200K and this is minus 200K. All right, I'm going to erase the amplitude here because the main thing we care about is the shape. Okay. All right. That's the answer I was expecting for part C. All right, for problem 2 on exam 2, we're looking at finding the upsample factor, which in this class we called that M. All right, so M, all right, let's start with, we know that M is going to end up being samples per symbol. So let's start with 90 kilosamples. Okay, so we want samples in the numerator per second. All right, and then if we divide by 3,000 symbols per second, we see that seconds cancel, just like any other units problem, and we end up with M being 30 samples per symbol. All right, so that's the answer on problem number 2. For problem number 3 on exam 2, we're looking at comparing two shapes. We're comparing shape P1 and P2, where this is P1, it's a triangle pulse, and here is P2, it's another triangle pulse, but we have different durations on the length of the pulse. All right, so it says in the problem statement that T2 is 2 times T1. All right, so as drawn, T2 is a longer interval than T1 by a factor of 2. Okay, so our options are A, the bandwidth of pulse P2 is twice that of P1. Well, if you make a signal with a certain shape, if you play it slower, all right, that actually uses less bandwidth than if you have it happen faster. Okay, so that one can't be true. All right, the bandwidth of pulse P1 is twice that of P2. It turns out, yes, that is true, because P1 is happening twice as fast. It's played twice as fast. If you think of it as an audio signal, it would be played twice as fast. Okay, so that's actually the answer. Let's look at these other choices. Bandwidth of two pulses is the same since they have the same shape. Well, the shape matters, but in this particular case, since they they have a different duration, the bandwidth is not the same. And it turns out both these are Nyquist pulses, so these can't be true either. All right, so the answer is B. All right, for problem 4, we're considering pulse shapes P1 and P2. Answer these true-false questions. All right, so the first one, we're looking at this. What is the bandwidth comparison between P1 and P2? True or false? The bandwidth of pulse shape P1 is greater than that of P2. All right, so what I'm thinking here is, first of all, P1 happens over a shorter duration. All right, so all things being equal, P1 would have been a higher bandwidth anyway. But this particular shape has a lot of edges on it, sharp transitions, which generates a high bandwidth type of signal. And so it's true. P1 clearly has more bandwidth, would require more bandwidth than P2. Okay? Next, we're considering the intersymbol interference. So looking at shape P1, one thing we notice is that over this interval, the center of the pulse, that's where you downsample, right? It's got a whole interval for downsampling, and the pulse doesn't extend over into other symbol intervals. So this would be, pretty immune to intersymbol interference. Okay, so P1 wins. All right, P2 extends over one symbol shape. Two symbol intervals, 0 to T and T to 2T. So we found we can still, that's a Nyquist pulse, because at the sampling times it doesn't interfere. But, if there's a little bit of downsampling jitter, it's going to have some intersymbol interference. Okay, so the answer on this one is true for both these. Okay, all right, next, I gave away the answers here, but next, consider pulse shape P1 and P2. Answer both these true-false questions. All right, so what I had in mind for you to notice on this one is that these are examples of raised cosine pulses. We've looked at those kind of shapes in class. All right. This one has a much more attenuated tails. All right. This one, in fact, looks like a sync function. All right, and so the advantage having this sync function with the ringing is that it's very bandwidth efficient. So in bandwidth, that one wins. All right, but because of the tails mean that the intersymbol interference immunity is worse. Okay, so in this particular case, the bandwidth of pulse shape P1 is greater than that of P2. That's true. All right, the rolled off tails give it a greater bandwidth. Another way to think of it, this looks like a sharper kind of transition. This one's moving along, and it rises up, but it's more a slow ringing effect, and so it's less bandwidth. Okay, pulse shape P1 is less susceptible to intersymbol interference because these tails are going down faster, so this one's also true. Okay, looking at the next one. We have pulse shapes P1 and P2. This looks like a sync type function. All right. This one extends over into 2 intervals, but this one extends over even more intervals. All right. So it turns out that, we talked about this in class, that when you go to raised cosine pulses and syncs, this is very bandwidth efficient compared to this. All right. So this one, although it extends over 2 symbol intervals, this extends over many symbol intervals. And so the bandwidth of pulse shape P1 is not as great as that of P2. All right, so that answer would be false. All right. Next, pulse shape P1 is less susceptible to intersymbol interference at the suboptimal sampling times. That is not true because of these tails. All right, so these tails extend over into several intervals. This one, the tails only extend over into one symbol interval. So on the scale that we talked about in class, P1 had less immunity to intersymbol interference than P2. All right, so that answer is false. Okay, in problem 7 on the exam, we were looking at considering a cost function, j of x, that is equal to 1/4 cosine squared of x. And our goal is to develop a steepest descent, I guess it would be ascent in this particular case, because we are maximizing the cost function. All right, so the way we start these, as we've done many times in class, is we look at the cost function and take the derivative. All right, so dj of x dx is 2/4, derivative cosine is minus sine of x, and the inside derivative is 1. Okay, so from there we need to update x. So the x of n update would be, you take x of n minus 1, and since we're maximizing, this would be plus mu times minus 1/2 sine x of n minus 1. Okay, so the 1/2 is not super important because this constant could absorb that, but this is the update equation that you would use for this algorithm. Okay, to answer the next question, we're looking at what would happen if you had an initial condition of about 0.1. So I've drawn a graph here already. This is what cosine squared looks like roughly. It's not exactly right, but we know that you square something, it's always going to be positive. The peaks are going to still show up where cosine is at a peak. So we should see peaks showing up at multiples of pi. Of course, cosine of pi is -1, but remember we're squaring things. So when that gets squared, it's also a peak at 1. All right, so if we started out with an x value around 0.1, we're close to a peak already, and we would expect to move to this particular peak, and we would expect x to converge to, or xn would converge to 0. Okay, so taking a similar approach, if we just copy this graph, okay, copying this graph, if we started out at something close to 3, all right, so right around in here, we would expect to see the algorithm step up to this peak that occurs at pi. All right, so in this particular case, xn would converge to pi. All right, now if we're using this type of approach to synthesize an oscillator, all right, so if we're doing a phase tracking kind of thing, for example, this initial condition would result in probably a sign inversion on the oscillator. We talked about that with the project, and of course the fix for that is to just detect whether or not you have a sign inversion, and if you do, you multiply by -1 to correct everything.
In problem 8, we're looking at a synthesized local oscillator signal that was generated by a Costas loop algorithm, and that's superimposed on the same time axis with the received signal. Okay, so clearly from the size of the signals you can tell that the oscillator is the one in orange, and you can then deduce that the received signal would be in blue. Okay, so what we're noticing here is that there's a mismatch between the peaks of the signal, all right? And so that would indicate that the synthesized oscillator signal, the local oscillator signal, is not synchronized with the received signal. So this answer would be false, okay? On the other hand, you look at problem number 9, we have a local oscillator synthesized by the Costas loop algorithm. This time the peaks are matching, all right? So each peak matches, and so this shows that this, at least for this time instant, the local oscillator synthesized by the Costas loop is in sync with the received signal. Okay, problem 10 takes a look at what happens with Costas loop phase estimates. Now, you should have seen this when you did your mystery signal project, and I think you'll recall that theta 1 from the mystery signal project converged to a straight line, and theta 2 converged to basically a constant. Okay, so let's go through these one at a time. On part A, so part A, the theta 1 estimate produces a straight line. Choose the best interpretation. A, this indicates the algorithm is not converging, and as a consequence the signal cannot be demodulated using the Costas algorithm. Well, we saw from the project that's not true. So we eliminate that one. Part B, this indicates that the transmitter oscillator operates at exactly the nominal frequency FC. Well, we talked about this in class. No, if the transmitter oscillator operates at exactly FC, we're just going to see a constant phase adjustment where we're trying to track the phase of the transmitter oscillator. So, because it's a straight line, we know that's not true. Okay, part C, this indicates the transmitter oscillator operates at a slight but significant offset from the nominal frequency FC. Yes, that's what we discussed in class. Okay, and then answer D. This indicates the Costas algorithm is affected by aliasing. Well, that's really just sort of a nonsense choice, so we'll eliminate that one as well. Okay, in part B, we're looking at estimating this frequency mismatch. All right, so I think the fact that I asked a part B would imply that the algorithm is converging. Okay, but again, you knew that from your project. All right, so what we know is that if we were taking a look at the transmitter and we know that we're operating at some offset frequency delta F plus some phase, all right, when you distribute this 2 pi through, we see that we have cosine 2 pi FCT, all right, so that is exactly the nominal. But then you have plus 2 pi delta f t plus psi. Okay, so this is the role of theta 1, and actually theta 1 probably has a constant term to it as well. So, you know, it's not exactly an equation of a line that goes through 0, but still the slope of it is what matters. Okay, and theta 2 would be more in line with converging to the offset psi. Okay, so if we look at the slope of the theta 1 line, we can estimate the frequency. So we know that 2 pi delta f is going to be y1 minus y2 over x1 minus x2, where I gave you the coordinates from the plot. Okay, so here's here's a y1, here's x1, here's y2, here's x2. Plug those in and you get a slope,
But remember, if you want delta f, you need to take this answer that comes from y1 minus y2 over x1 minus x2 and divide by 2 pi, and you will get the answer in hertz. Okay, so when you do that, it turns out to be approximately 500 hertz. There's the solution to problem number 10.